Hi everyone, my name is Freyberg, and I work at a company called Element AI, and I'm here today to talk to you about active learning in the interactive Python ecosystem. I work at Element AI, which is a Canadian startup based in Montreal, and we build products based on artificial intelligence in general, and in my team, products for AI for good in particular, so applying machine learning and artificial intelligence to problems that NGOs or other sort of organizations that are tracking things like abuse online are doing. And so, for example, we work on finding abuse online. On Twitter, we had a big project about misogynistic abuse on Twitter. We're working a lot with satellite data on spotting destruction, in particular in Sudan. And we also work with organizations like Forensic Architecture, which is a group at Birkbeck University, on accountability in weapons. So we're tracking these tear gas canisters in the bottom right, for example, in online media. Mostly using computer vision and natural language processing. I work on the computer vision side, so most of the examples today will probably be based on computer vision. Yeah, and so just to give a quick outline of the talk, most of it will be around acquiring labels for your data and doing so efficiently, how to do it in Python, because this is a Python conference, and then how we can scale that a little bit. And I've been interested in this for a while. I'm interested in interactive computing in general and active learning in particular because when we do projects like this, we often need labels, and those labels are often provided by volunteers. And so the more efficiently we can do it, the better. So I'll quickly talk about why we should label data. So in general, I'm sure most of you are familiar with this sort of dichotomy in machine learning between unsupervised and supervised machine learning. In unsupervised machine learning, we kind of try and infer structure in the data. So we see where the sort of modes of the data are, where we can find clusters, and we'll use that to then group data points into clusters. Whereas with supervised machine learning, if we have some information about the data, such as which points are blue and orange here on the right, then we can use that to build classifier models, for example, that are dividing the data into these two. But that means we need labels, right? We need to actually know which of these points are blue and which of these points are orange, or at least which subset of these points are blue and orange, in order to be able to train our model. And so labeling data really is moving from this unsupervised paradigm to supervised machine learning. There are lots of reasons to do that. Supervised machine learning can be a lot more powerful than unsupervised machine learning, and in particular, if you already know that you want to classify data into specific groups rather than let an unsupervised algorithm find clusters or groups within your data, then you ideally want to end up in this supervised machine learning paradigm. But labeling data can be expensive, it can be difficult, and it can be slow as well. And for those of you who were here in the talk just before, it was a geophysicist talking about acquiring labeled data by actually drilling down into the earth. So obviously that costs a lot of money and it takes a lot of time. And really, what we want to do is do this efficiently, because ultimately labeling data is also essential. It's very important for a lot of people's work. And maybe just as an example for this, I do a lot of computer vision, and so one of the sort of seminal papers in this is this paper that first showed state-of-the-art performance of neural networks on computer vision tasks. And that was done on the ImageNet challenge, which probably a lot of you are familiar with. It's a huge data set of images which were labeled by people, classifying them into what is actually depicted in the image. And there are hundreds of thousands of these, and it took a huge amount of work to produce that data set. But now that we have it, we can benchmark algorithms against it, and we can train these new state-of-the-art models that make use of those labels. So labeling data is pretty good. Cool. But given that it's slow and can be expensive, you might have to pay people to actually sit there and label your data. How can we do that efficiently? And hopefully from the title of the talk, you know that I want to sell the idea of active learning to you. So in general, the labeling data process looks a bit like this. You get some people to label your data, and then you train a model and maybe check the model's performance. And if you want to improve your performance, then maybe you label some more data, and you kind of go around until you reach either the end of your labeling budget, or you've sort of achieved the performance that you wanted to achieve and are happy with it. Cool. So the active learning circle adds a few elements to this. So in active learning, we usually start by labeling some data, just as before, and we then also train a model on this labeled data. So just as before, and that means we can also benchmark it, see how it performs, and see whether we're satisfied with it. But then we actually use the model that we've just trained to start making predictions on the rest of the data that we haven't yet labeled. So in the case of images, if we've labeled 10% of our images already, we use the model that we train on that 10% to make predictions on the remaining 90%. And then we use those predictions to create ranking of that unlabeled data. And that ranking is really sort of the priority in which we want to label that data. And the real sort of benefit in this comes from the fact that when we rank the data using the predictions of our model, we can try to select the data that will be most informative to the model and hopefully will most improve our model. So because the model is sort of telling us a little bit about what it interprets the data to be, we can use that information in order to provide maximal information to the model. And then we keep going around, so we then go take that ranking, send the top maybe 10% to our labelers, get them to do some more labeling, and then keep going. No. The ranking is not manual. So, and I'll talk a little bit about that in a second. Just to sell you maybe on the commercial case of this, we at Element AI work a lot with image data, and in some of the cases, we've sort of reduced the amount of images that we need to label in order to achieve the same performance of our classifier from 10,000 to 4,000, or from 7,600 to 3,600 images. And so with active learning, you buy one label and you get one free because you're reducing the labeling load by half in some cases. So it's a really powerful commercial tool. And in the case of AI for Good, it means that you have to use less of your volunteers' precious time to produce labels. Cool. So how do we actually do the labels? Like your question, how do we actually get the ranking of the data based on our model? So imagine that we've got some data that already has some labels. So here we've got points, which are either green or red. And we've already got two labels. We've got one point up here, which is red, and one point down here, which is green. And we want to classify the remaining points. And because this is a fairly simple problem, and we've only got two features, x and y, we can actually fit a fairly simple model. And in this case, I've just drawn a model in the middle of this. And so now, what we want to do is basically choose the data points about which the model is the most uncertain, right? So we have a point up here to the right, and the points close to it are probably more likely to also be red than the points very far away from it. And likewise, the points in the bottom left are more likely to be green. And so ideally, what we want to choose is points about which we actually, or about which the model currently doesn't know very much. So we want to choose the points about which the model is uncertain. And with this fairly simple model, it's pretty straightforward. We can just choose a point that's close to the decision boundary of the model, right? So this point in the middle, we actually know that the model, if the point was shifting just a little bit to the right, then the model would have classified it as red. At the moment, it's classifying it as green. Really, we know that the model is fairly uncertain about this data point. And so that's how we generate the ranking. We choose the points about which the model is uncertain, and then we get a label for that point. So now we know that this is a red point, and we've retrained our model, and we've shifted the decision boundary, right? So now we have a new model, which hopefully does a little bit better than the previous model, and we can now repeat this process, because now we have a new decision boundary, which cuts the data in a different way, and we can choose points based on that decision boundary again. So in this case, we label that point. It turns out to be a green point. We're shifting the decision boundary again because we're retraining the model. And so now we've got a very different looking model to the one we had before. And we've selected points which are hopefully useful to the model. And they've, in fact, shifted the decision boundary by quite a lot. And we can then keep going with this and repeat it until we reach the performance that we want. So that's the general idea. It's very easy to draw out on paper like I've done here. But in many cases, we don't actually know the decision boundary of a model, right? So if we have a complex model in computer vision, we have convolutional neural nets, which make decisions that we can't analytically find the decision boundary for, right? So we don't know which pixels need to be shifted in order for this model to now classify this image as a different category compared to what it is right now. And so what we can do instead is we can use two different approaches. One is heuristics and one is approximate posteriors, and I'll quickly talk about both of them in order to make this ranking. So heuristics are generally based on continuous model output. So if we have a convolutional neural network, which is classifying the MNIST data set, which is just some handwritten digits, and the challenge is usually to classify it as one of the digits between 0 and 9. And then we make a prediction with a model. So we call .predict on this number down here, on this 5. And then we get this output, right? And this is the probability of each of these digits. So the model is currently claiming that it is, giving, or it's assigning this probability to the number 6, and it's assigning this probability to the number 0. And then we call the model on a different number. And in this case, it's assigning most of the probability to the number 4 and very little to the other numbers. Realize I actually took quite a bad example because this is a 5 and it's assigning nothing to the 5. But just imagine that it was the other way around. So now we've got a model and it's telling us something about this data, and we don't know the actual labels for this data right now. So how can we distinguish between these two? How can we decide which one we want to label next? So one heuristic approach is to just take the margin between the top and the second highest prediction. And so in this case, for the number on the left, it's between 6 and 0. It's assigning some probability of 0.27 to 6 and 0.25 to 0. And the difference between those is 0.02. And for this number on the right, that difference is much larger because most of the probability has been assigned to the number 4. And so that's one way we can rank the data, right? We know that the model is relatively certain about the image on the right because the difference between those top two predictions is very high. And then another approach is to take the entropy of this categorical distribution. And again, we can see that the entropy on the left is much higher because it's assigning a lot of probability to different categories. And on the right, it's very low because most of the probability is in one category. And so again, we can use this to rank the data and decide which one to label. And so this is a fairly nice approach because it works with any model that produces probabilistic output, right? It works with any model that gives some probability for each category. But sometimes we don't actually want to use that. And in particular with neural networks, often neural networks are way, way too confident about the data. They're not very well calibrated, and they're giving really confident output for predictions that are completely wrong. And so that's not nice and would not help us when we decide what to label. And so instead, what we want to hopefully end up with is approximate posteriors. And so now, instead of assigning one probability to each category for one image, we're assigning a distribution of probabilities. So that's what we want to end up with. How can we actually do that? One way is to use Markov chain Monte Carlo in order to get sort of approximate posterior distributions, but that can be quite difficult. You need a sort of fairly well-defined model, and it's often not that fast if you've got a lot of data. And so the other thing, which I work on a lot, is approximate posteriors in neural networks. And two approaches here, there's lots of them, but just two that I wanted to highlight is if you're training a network and it has some probabilistic components like dropout layers, then you can actually use those components in order to generate distributions of output. And so this is known as Monte Carlo dropout, where you just make many, many predictions for one image, but you change the units in the network that you drop out at each point, and so that gives you a distribution of output. And similarly, you could model the weights in the network using the samples from your stochastic gradient descent. So usually we train a model, and this is the loss surface, and we're kind of trying to use gradient descent to arrive at the minimum of this loss surface. But if we actually assume that this stochastic gradient descent is somehow exploring this posterior distribution, then we can take samples from along the way and use that in order to produce, a probabilistic neural network, basically. So that's just two approaches that I work with a lot and that have been pretty successful. Cool. So I've given you sort of the background for active learning, and I've told you why it might be useful for you. But what you actually need to do active learning in Python. And just going back to this circle that we're trying to sort of fit, we first need to label some data. And in order to do that, we really need a Python process that acts as our backend, right? And selects our data, loads it from some database, for example, and maybe also fits our model. And then we also need an interface or front end for this labeling process, because especially when we're using images, we need to show the images to a user, and they need to be able to click a button that determines its category. And so this front end is just going to display that labeling UI to our users. So luckily, we actually have a really good framework for running a Python process as a backend and a web interface as a front end, right? And that's the Jupyter framework. And I've developed this library called Superintendent, which leverages that and the sort of IPy widgets framework, which is sort of matched Python objects and JavaScript front-end objects that allow you to interact between the front end and the back end in order to do this labeling. And I'm just going to demonstrate this. So this is a Jupyter notebook, right? A lot of people are familiar with this. It's a combination of code and output and some markup that we write around it. And what I'm going to do is I'm going to load the MNIST dataset from scikit-learn. And this is the digits that I showed you on the slides earlier. And what we want to do is we want to classify these as one of the digits between 0 and 9. But we don't have any labels, right? So we need to start creating some labels. And so all I'm going to do is I'm going to use this class from Superintendent to generate a widget. I'm going to pass it the features of this data, which is just the actual pixel values of this image. And I'm going to also, because I know these are the digits between 0 and 9, I'm going to give it the options that I want to have displayed in my framework, in my UI. And when I do that and then display this widget, we've got a labeling interface. So now we're seeing the digits, and we've got the buttons in order to classify this data. And I can start labeling it. In the beginning, it's quite easy because they're actually ordered. So I can just hit all these buttons, and you can see the progress as we're going through this data set. And we're racing ahead. Cool. If I ever make a mistake, I can also undo it or skip one of the images, because maybe I can't recognize what it is, like this. Is that a 3 or a 9? It's a 9. Cool. And so now we've assigned some labels to this data, and I can access that as an attribute in this widget class where we've assigned all of these labels. This one we skipped, but we've got some label data now, so we can start using that. So the next step in the active learning circle is we need to train our model, right? And we need to make predictions on unlabeled data. And I'm not going to talk too much about this because there's a huge amount of frameworks to do model fitting in Python, and you could probably run a whole conference about that alone. But just one thing I wanted to highlight is what Superintendent makes a lot of use of is this scikit-learn interface for models where you have these fit and predict methods on model classes that are fairly uniform across different types of models. So we can do something with logistic regression, and we can do the exact same thing with random forests. If we're using the scikit-learn submodule of Keras, we can just do that with a neural network as well. And similarly, for PyTorch, there's frameworks that sort of construct this interface for neural networks as well. And we just always have to use these fit and predict methods if we have our model defined. And so obviously for MNIST, the state of the art at the moment is a logistic regression. So we can just import that from scikit-learn, and we can fit our model using this .fit method, and then we can start making predictions on our data. And just because earlier I showed you that we need probability output of these models, we can use this probability prediction method instead in order to get this continuous output on how confident our model is about our data. Cool. But then we actually want to bake this into the labeling process, right? So we want to have a sort of uniform circle where we can do this entire process of training a model, making predictions, ranking the data, and then labeling some more data all in one go. And similarly, we can do that in Superintendent. Because of the niceness of these interfaces, we can create a new widget. I'm going to take over the labels from the previous widget. So if you have some labels that you've already generated, you can just pass them into Superintendent objects. And I'm going to pass the model that we've just trained, this logistic regression model. And I'm going to say that I want to reorder using the entropy. So what I showed you earlier, right? The entropy of the distribution of the model output. And so now we've got the same widget, but we've got this extra button up here, which we can use to retrain our model periodically. It will show us some performance output of our model as well, using cross-validation. And we can, once we do that, reorder our data based on the uncertainty of the model. So I'm going to assign a few more labels and then retrain our model. We don't have enough labels to do proper cross-validation yet, so we're not evaluating that. But we have now reordered our data, and we're now seeing really less clear images, which is nice already. And we're exploring a space in the sort of feature in the data set that the model is, as of yet, pretty uncertain about. So clearly a lot of 8s. I think that's because we skipped the 8 earlier. Cool. And we can just keep doing that and keep training our model. 7, I think. OK, great. So we've got that going. So now I've showed you how to do that, how to do labeling, just using the tools that you already know, Jupyter Notebooks, widgets, which are pretty common and work really well in Jupyter Notebooks, models that you're familiar with, scikit-learn, Keras, PyTorch. So now the question is, how can we scale this? Because what I was doing here is fitting a fairly simple model that is very quick to train. The data was pretty straightforward as well, and I could just do that by myself, hitting the retrain button whenever I want to reorder the data. But in practice, you probably want to send out your labeling tool to a bunch of people who will do the labeling for you, so that A, you get maybe less biased mistakes by the same person, and B, you're just not doing it all by yourself and getting bored. So how can we scale this process? And so what we really need to do for that is we need to share some information in between the labeling sessions, right? So here I was running a Python process just on my laptop. It's pretty hard to share the information from that process with somebody else's laptop who's running, who's also doing labeling on the same data set, just because it's hard to tell them which points I've already labeled. It's hard to tell them what my model is currently saying about the unlabeled data, etc. And so ideally what we want to do is run the model fit on a separate server. That also allows us to scale that server arbitrarily. So if we're fitting a neural network, we can have a much bigger instance that has some GPU power in order to do that. And then we want to just have a single ranking of all the unlabeled data for all labelers, so that we're sort of not wasting any energy labeling labeling data twice or labeling inefficiently for one of the labelers. And so the sort of framework looks a little bit like this. We're going to use a database in order to manage this queue of labels to generate and also to store the data so that not everybody has to have the data on the laptop. We can use a server in the top left in order to run the model and add data whenever we get new data in. And then we can have a bunch of people in the bottom right doing the labeling for us. And I'll just quickly show how I've done this in the past in a really successful way, using Docker and using a tool called Voila, which is fairly new, I think, but which basically takes a Jupyter Notebook and displays it as just a website without all the code and without having to run every cell yourself in order to get to the output. And we're just going to manage the data in a Postgres database. So where have I got this? Here. So we've got what we want to do is we want to run one script which actually does the orchestration of this process for us. And this is this orchestrate.py script, which basically we're defining a model here. And what we're going to do is create a database connection to a Postgres instance to this database called Superintendent. And then we're basically going to connect to this database. I'm going to do this with Docker Compose. That's why I had to do this while loop, because otherwise, if the database doesn't come up, everything fails. And then we're just going to run this orchestrate method on our widget. So this widget will never actually be shown to anyone, but because we're basically defining a model in exactly the same way as we were when we were doing it interactively, we can still use this widget in order to sort of have all the nice utilities of reordering the data and fitting the model regularly. And we're just going to say that we want this model to be fitted every 30 seconds and only when there's 10 new labels in the database. So what we want to do is run this script regularly. And at the same time, we want to then run a user interface for the labelers to actually start labeling. And so what I have for this is a notebook which is a lot thinner than the one I was using to demonstrate the capabilities. So all we're going to do is import the same widget, but from the distributed submodule of Superintendent. And we're just going to pass that same database connection in. And we're also going to say which options we want to display to the user. And then all we need to do is actually display this widget. So that's what this bottom cell does. Cool. And so the way we're going to do that is using Voila. And I'm going to run this using Docker Compose, just to show you that it's quite nice and easy to bring up the database and generate the UI for everyone at the same time. So we're just going to bring up a Postgres database here. And this is just a UI for the database. And then we're going to run one server for our notebook. And this is going to use this Docker image that has Voila installed and basically mount this notebook that I just showed you into a specific location in the Docker image. And then at the same time, we're going to run one server which runs this orchestrate script. So we've got kind of a separation in between these two. And if we're doing this on a cluster, then we could split divide the compute unevenly between this and have a much bigger server for the orchestration script. Cool. So this is all not very much code, which is kind of nice. And it will allow us to bring up these 4 servers pretty quickly. So I'm just going to run this. And this is going to start the database server for us. It's also going to start the notebook server for us. So that's this purple one here. The database is coming up. And the orchestration is already happening in the background. And so now I'm just going to have to wait for Voila to come up, which I think will be on port 8866. Yeah, there it is. And so that's a matplotlib bug. This cool, this fairly simple notebook, which I just showed you, is now displayed as a website that doesn't have any of the associated code or anything else sort of around it. So we can run this, or we can send this URL if we were running this on the web server to colleagues who can do the labeling for us. And as you can see, preparing this talk, I've already done some labeling, so we're already progressing quite a bit through this data set. And I can just keep going with this now. And in the background, the orchestration server is ordering the data. Clearly, at the moment, 4s are needed in order to improve this model. And I don't even know. And we can start generating more data efficiently without having to worry about training the model ourselves or even defining the model. And yeah, if we wanted to scale this up, at some point we could swap in the logistic regression for a convolutional network or whatever we want to use in order to classify this data. And that sort of, yeah, makes everything a little bit easier for the people. We've used this really successfully in the past. My previous job used this library and this way of orchestrating these notebooks in a really big image classification problem. We've also used this for time series classification, so showing a specific sort of time series plot to people and asking them whether this fits into one of the categories that we had predefined and wanted to distinguish between each other. And yeah, it's fairly flexible because it all uses the Jupyter ecosystem that you're familiar with and like, hopefully. Cool. So yeah, you can install this library, and there's documentation up online. In particular, the deployment is fairly new, so if you want to try that out and let me know how it's going, then definitely do. And yeah, that's it from me. Thank you very much. Cool, so I'm a little bit early, so we've got a lot of time for questions, if you have any. I think there's a microphone, or there will be a microphone circulating in a second.
How is there overlap between different raters handles? So is it, can you define that as you say you want? So I'm wondering, how is sort of multi-rater reliability handled? Like, can you define you want at least like 3 raters to rate the same thing, or 5 raters? You want that sort of Cohen's kappa or whatever? Is that part of it?
It should be. It's not yet. That's one of the things that I want to work on next. Yeah, getting multiple people to rate the same data point or label the same data point, and then modeling the agreement between them is definitely something that I want to include in this because it's pretty useful to do. Yeah, I don't have a way of doing that at the moment just because the way the database tables get set up doesn't allow it at the moment, and there's like a little bit of extra modeling work to do in terms of the agreement, so it's going to come. But yeah, if you have any experience with that, then definitely contribute or let me know or talk to me.
Thanks.
Do you have a way to handle erroneous labeled data?
No. So this doesn't have a way built in. There are obviously lots of ways of doing that, and at the moment that needs to be handled by the user. You've got full access to the sort of database once it's created, so you can actually inspect the labels and fit whatever other model you want in a separate script or notebook or whatever. But yeah, that's not included in this at the moment, unfortunately. Yeah.
So when you mentioned the ranking, it sounded quite deterministic in terms of like getting your ranking, you pick the one at the top or whatever. Is it really deterministic, or is the choice of which label to label, which data point to label a bit more stochastic in the sense that maybe your model's slightly misspecified and you don't want to just always pick the one that you think the model is?
Yeah, that's a really good question. So the ranking in general is deterministic, right? So the entropy of the predictions will always be the same if you have a deterministic model that doesn't, change its output between different runs. And that can be a problem, definitely, because if your model is biased, then the ranking will be biased as well. And so the way we solve that here is actually we have a shuffle proportion where you can just specify, I want this number of data points to be shuffled each time we create the ranking, just so that you still have some randomness and hopefully can maintain a representative sample. Yeah, in general, that's a problem in active learning, right? Because if you're creating a data set for a specific model to improve that model maximally, then you don't actually know whether that model will also transfer to other models. And so that's something that shuffling some of the ranked priorities can achieve. Yeah.
Thank you for a very nice talk.
Hi.
The widgets that you were using,
Yes.
labeling, are they more at the level of if I have an image, could I select a region of the image that I want to label, or if it's a time series, a specific feature within that at that level of flexibility of parts, sub-labeling almost, I guess?
Very good question. That really depends on the ecosystem. So the framework is fairly flexible in that you can, if you have, okay, I killed the Jupyter server, but if you have some other way of displaying the data that's not images, you can actually use any widget that comes or that interfaces well with the IPy library, which is this one here, in order to display the data and get the user to give input. So I work a lot on object detection in addition to image classification, and so getting some boxes around parts of an image would be really nice. I haven't found a good way that interfaces well with Superintendent to do that yet. And at some point I was planning to do that myself, but it's quite a lot of JavaScript work, and I don't know JavaScript that well, so yeah, not yet. But yeah, in general, it's pretty flexible.
So when you're running this cycle of labeling and splitting, how do you know when to stop? Is there some kind of convergence measure where you decide, okay, we've done enough labeling and any more is not going to help?
Yes. So, well, that really depends on the business problem that you're trying to solve. So if you just want to get to some accuracy or some performance of your model, however you want to define that, then you can just run this until you reach that point, and you've got the labels now in order to test the model, so you can do your splits of the data and stuff. There's also, you can also just decide to terminate it once you reach some plateauing effect of the performance of the model. And really, that's completely up to you. So I haven't implemented any of that here, but you can do that yourself. Yeah.
All right, we've got time for 2 more questions. Hello. Yeah. So every split is gonna cost you in retraining, especially if the model is quite big. How do you determine, or do you have any framework to determine how many splits you would need to do? So I guess what I'm saying by split is you have some data, you ask for more data, you ask for data, you ask for more data. If you do that too many times, then it's going to be very inefficient. So
yes.
How are you measuring that? What's the most efficient way of doing that?
Again, that's really up to the user. So that's not something where you can just define some metrics a priori for that. And it really depends on the cost of your labels, the cost of your retraining, and how long it takes to get new labels. So if every time you want to get a real label, you have to drive out to the desert and drill into the core of the earth, then obviously you don't want to do that too often. But if it's just getting people to click some buttons, then maybe you want to rebalance that a little bit and get 100 labels for every time you retrain the model. Yeah, it's completely up to the user to define that balance. And for us, we basically rerun the model all the time because we've got a lot of GPUs sitting idle in Canada. So yeah.
Okay, one more question.
So have you thought about sort of interfacing with mechanical Turk, or do you get volunteers programmatically?
I have, yeah. That's definitely on the roadmap as well. This sort of serving notebooks as a website is a fairly new thing that we're able to do. And so I haven't developed that in any depth. Ideally, what you would need for that is to be able to parameterize the request to the notebook depending on metadata from Mechanical Turk. And I don't think that's implemented yet for notebooks. At some point, I was thinking about maybe implementing a different front end for this that uses something like Plotly Dash or something where you have a proper web server. But I think what people really want is to be able to switch very easily from the notebook to the labeling session, and so we haven't done that yet. Yeah.
All right, thanks, Ian.
Thank you.